Morning, everyone. Thank you, Lanai. Very happy to be back here. Still remember all the meetings we had at the beginning of this Barnegat Bay initiative. So cannot believe, right? It has been like more than 10 years. But I'm very excited to share all the progress on the Plan 7, which is adopt more rigorous water quality standard. I'm going to cover the monitoring, modeling, and also the total nitrogen target development. This way. Okay. All right. Lanai already talked about the purpose for Plan 7 a little bit already. So where this Plan 7, we want to have a better understanding of the water quality within the bay, the extent and then the location of the impairment. And also we want to build a good model which can predict the situation within the bay, direct us to for the TMDL development. And based on the response to the pollutant load and also the water quality target we pick, we will be able to identify loading reduction from various sources and guide the restoration effort to achieve the improvement of the water quality within the bay. So start with the monitoring. People always ask, why you need more data? Yes, we do have data. We have all the data, we have the historical data. But when we took a closer look of those data, we noticed that they were not collected from the same time frame, and they do not have a good spatial coverage. And then when you check the parameters or the analytical method, they were not consistent. Okay. And then from the modeling developer perspective, we do need a comprehensive data, which, ideally collect from the same time window and from the location, which are spatially representative. And also, we need not just the water quality data, we also need the flow data. So that's why we designed this target monitoring. We want to have a unique data set which will serve us not just to have a good water quality assessment, but also to support the model development. The target monitoring, it was from June 2011 to June 2013. And then we did both flow monitoring and also water quality monitoring. The flow monitoring was conducted together with USGS. It's along the tributary, also within the bay. Along the tributary, we rely on the gauging stations and also manually sample flow. Within the bay, we rely on the gauging station and also the tide gauge. For the water quality sampling, we actually get more partner involved. So we did a discrete sample. We also deploy buoys to get the continuous monitoring data. We also have a special event we call the intensive sampling event. I will talk more about that in the following slides. So this map shows the station where we collect the flow data. So we have a total 17 gauging stations. 7 of them along the tributary, 3 of them is at the Bay Inlet, the Little Egg Harbor Inlet, Barnegat Bay Inlet, and the Point Pleasant Canal. We have 3 gauging stations in the bay, which along the bridge, the Mantlocking Bridge, the Route 37 Bridge, and Route 72 Bridge. For the tributary station where we do not have a gauging station, we collect the flow manually when we went out to take the water quality sample. This map is show the water quality monitoring station. We have a total 12 tributary stations. So as you notice, we use BT. So B is the Barnegat Bay, T is the tributary. So we number them from 1 to 12. That's from north of the watershed to the south of the watershed. So BT1 is the Matiticon, and then the BT12 is the Westcon Creek. We took the grab sample. For most of the station, we took the grab sample, but we do have one fixing station, which is one fixed continuous station, which is at BT03. That's the Toms River at Toms River. We have 15 stations within the bay, so that's a good spatial coverage. For most of them, we went there on the boat, take the grab sample, but we do have 4 buoys we were able to deploy to get the continuous reading for certain parameters. That's temperature, DO, and specific conductivity, and the chlorophyll A. For the discrete sample, we did collect the field parameter, same as the buoy is the temperature, DO, pH, specific conductivity, and we were able to calculate the turbidity. But we also send the sample to the lab to analyze a suite of parameters. For those suite of parameters, we pick based on our research for other estuary program when they develop their eutrophication model. You know, he does mention the eutrophication, so that's the eutrophication model we evaluate, and that's the suite of parameters we decide to analyze. So that's total nitrogen, that's nitrogen species, phosphorus, silica, TSS, chlorophyll A, BOD, and then organic carbon. For most of the sampling we took, we call the discrete sample. So it's the frequency varies a little bit. During the growing season, that was a weekly sample, and during non-growing season, that was bi-weekly or monthly sample. It's basically we went out to collect 1 sample per day at that station. We also have that intensive. Why we call intensive? Because that is the event we went out to collect 6 samples in the same day. And then it ran 4 days per event. So we had 3 intensive events, 2 in 2012 and then 1 in 2013. So this is the scope of the intensive monitoring. So we did that in 27 sampling locations within the bay and along the tributary. We had 6 boats involved, and there were 13 sampling teams. And then it's 75 people per day get involved, and we collect more than 4,000 samples through the intensive. The reason we want to do the intensive, we want to check, is there any daily variability of the water quality? This figure shows the sample collection and the transport logistic. So you can see on the boat, that's the monitoring on the bay. And then by the bridge, that's the tributary monitoring. So we have different partners help us. And then after sample being collected, they will transport to the FRAC, our lease point lab, to processing, because some sample we need to do the dissolve phase. So we have to get the filtration done there. So after the sample were filtered or preserved, they were sent to different lab for different parameters to be analyzed. We have a total 5 labs involved. So I have all of them listed here. So most of the analysis was done at the lease point, but we have the Ocean County Utility Authority to analyze the BOD. We have EPA Region 2 Edison Lab to analyze the silica. And then Maryland University Lab, they analyze the organic carbon from the saline water. And the Department of Health lab, they also help us to analyze some samples. In addition to the lab, we also have other great partners, 11 of them. They help us to collect the sample, we're processing the data. So that's all the logo of all the partners. So, we are very, very grateful to all the great contribution the partners put into this monitoring effort. We know without them, we would not be able to collect that many data in such time window. So, thank you. I just want to give you some quick review about the data we collect during that period of time. So in the following 3 slides, just the total nitrogen concentration. The first one is the average concentration of total nitrogen along the tributary stations. So it's, as you can see, BTO1, that's the Matiticon, and then I'll go all the way down to the southern part of the watershed. Clearly, the total nitrogen concentration in the northern part of the watershed are much higher than the concentration in the southern part of the watershed. But interestingly, you notice the BT11 has a higher concentration compared to other tributary in the south. BT11, that's the Mill Creek. The concentration of the total nitrogen in the northern part of the station is around like 0.8 or 0.8 to 1 milligram per liter. Remember, we collect the flow. Why we need the flow? Because when we have the flow, when we have the concentration together, we can calculate the mass of the nitrogen enter into the bay. So this is the total nitrogen loading from each tributary station coming into the bay. So this, even though, the BTO1 had the highest concentration, but since BTO3, which is the Toms River, they have the highest flow, so therefore, the highest load of total nitrogen come from Toms River. We also look at the in-bay total nitrogen concentration. So as you can see, the highest concentration, that's the right dot on the map, that is BBO4A, so that's by the Toms River estuary. So in general, the total nitrogen concentration in the bay is higher in the northern part of the bay than in southern part of the bay. But we do have some relative hot spot in the southern part of the bay. As you can see, the green dot on the map, that's BB11 or BB10. Okay, so that was the target monitoring. That's for those two years. We did not stop monitoring after that. We actually have been conduct long-term Barnegat monitoring since 2013. We developed a QAP every 5 years. We made some adjustment on the sampling location or sampling frequency, but we already finished 2 of them. So that's 2013 to 2018. That's the first 5-year long-term monitoring, and then 18 to 23. That's the second year. Right now, we're just the beginning of the 3rd year, 5-year monitoring. Bob Schuster will talk more about that in his presentation. Okay, so we have all the data, and then the data is for the good use. Per the Federal Clean Water Act requirement, each state needs to submit an integrated report every 2 years. That integrated report is to assess the quality of water across the state for the designated use, which including the aquatic life, recreation, water supply, fish assumption, and then shellfish harvest for consumption. So using the data we have, we need to compare the data to the applicable water quality criteria. If the reading is beyond the limit set by the criteria, that means a violation happened. Given the frequency of the violation, if the frequency of violation exceeds the threshold, we will consider that water body is impaired for that parameter. We use the data we collect from the Barnegat Bay, and then we compare the applicable criteria. So this is what we have from the 2022 integrated report, the assessment result for Barnegat Bay, both watershed and the bay itself. The first one on the left, that's the dissolved oxygen. So you can see that we have a bunch of dissolved oxygen impairment, but only one of them is in the in-bay assessment unit. That is the Matiticon estuary. So this is, it's on the top part. So maybe you cannot see clearly since that's next to a tributary assessment unit. But for the turbidity that's on the right side of the map, we have 3 assessment units within the bay are listed as turbidity impaired. For those impaired water body, we put them on a special list we call 303D list. So the Clean Water Act requires for any water body on the 303D list, a TMDL needs to be developed to ensure that the water quality standard can be attained. So what is a TMDL? So TMDL is the total maximum daily load. It's both a quantitative assessment of pollution sources and pollutant reduction needed to restore and protect water, and a planning process. So planning process for attaining water quality target. You consider various source for the loading. This gave you idea about TMDL development process. So the first one is say when the water is impaired, and then the second one we need to assess the pollutant source. The third one is we need to construct a model, or we need to find a technical approach to figure out what's happening, right? And then the next one is we need to determine the appropriate source reduction. And then we need to do the implementation in order to achieve what we want. So that's about half of my presentation. I don't know if you have any question I can answer before I move on. Yeah. That's a very good question. Yes, this TMDL is targeted on to achieve the water quality target within the bay. So we are going to require the reduction of the loading coming from the tributary. So when we achieve those reductions, it would definitely help to improve the water quality along the tributary. And then we do have some study going on within the watershed, and that will help us to check the improvement on those areas. Yeah.
Good morning. We have 2 questions online in the chat. So we have one from Christian Mansilla that says, good morning. Did you collect vertical profiles of water quality, like temperature, DO, and chlorophyll?
So for the dissolved oxygen, you mean the threshold? That's the value we use? Is that the question?
It's more general than just DO. I think it's just saying for all of the parameters. For any parameter, did we take vertical profiles?
So you mean collect the sample? We do have, for some stations, we collect the both surface and the bottom.
Okay,
Yep.
yes, okay, I think that answers the question. And then from Paul Shore, what is the flushing rate?
I'm not sure I will be able to answer that question later. I think the flushing rate means the residence time within the bay.
Yes.
I will be able to answer that in the following, in the second half of my presentation.
Okay. Yes, all right, and then one last one from Robert Nicholson. Do loadings include nitrogen from the ocean coming in through the inlets?
Yes, yes, that's a very good question. I will also talk about that in my modeling session.
Great, thank you.
Yep. Thank you. I'm going to move on. Okay, remember in the TMDL development process, and then the third one is we need to come up with some technical approach, maybe a model to understand what's going on, right? So what is a model? A mathematical model is an idealized formulation that represents the response of physical system to the external stimuli. We normally, we have water quality model, which is to simulate the pollutant, the fate and the transport of pollutant within the water body. We also have a hydrodynamic model, which is to simulate the movement of the water. Model always sounds like, like a scary term, but actually we do have model in our daily life, right? Today is a cold day. I don't know how many of you actually check the temperature. So the weather forecast, that is the model. And then, sometimes we are all care about the air quality. So the air quality modeling is also a model in our daily life. And the model could be simple, could be complex. I don't know if you use any spreadsheet, the spreadsheet calculation can be called as a model, even though it's simple. But most of the time when we talk about model, it's a complex model. For Barnegat Bay, it's such a complicated system, right? So we want to have a good understanding on what's going on spatially and temporally within the system. And we want to know how the bay will respond to various loading. And we would love to answer some what-if scenario and then be able to predict the future situation. So that's why for Barnegat Bay, we need a complex dynamic model. This schematic shows the Barnegat Bay work and its relation to modeling and management. So in the middle of this, that's on the left, the hydrodynamic model, and then on the right, that's a water quality model. And on the top that, for the hydrodynamic model, you see we have the flow monitoring, we have the sea floor mapping, so that's the bathymetry survey we did. And also we did a sediment study. We got some information from the sediment study, which was put into the hydrodynamic model. For the water quality modeling, all the water quality data we collected was entered into the water quality model. And also we obtained some information from the research project that was part of the input as well. We have the air deposition that is all provide useful information to the water quality. So with the model 2 setup, that will allow us to do the management decision. Lanai talked about some of this already, but I just want to repeat here. In addition to the model development, we did do other studies to support the model So the bathymetry survey. And then we also establish an air monitoring station within the watershed, so that will enhance our estimation of the air deposition loading within for this specifically for this model. We had the bathymetry, nutrient flux, and the sediment oxygen demand study. We also correct the suspended sediment concentration and flux. That was able to improve our boundary input, and that was helpful for the model calibration. We also did the shallow water sediment resuspension lead attenuation study. That's the parameters we were able to plug in to set up the water quality model. And all the 5 projects, they were conducted by USGS. Okay, so that is the 3 parts of the Barnegat Bay modeling. Let's start from the bottom part. The bottom part is the hydrodynamic model. And then using the linkage file, the output from the hydrodynamic model was able to be sent to the water quality model. So the hydrodynamic model simulates the water level, velocity, and then the circulation pattern, and also the temperature and the salinity. All those information were processed by the linkage file and then passed that to the water quality model. We use WASP as the water quality model here. And then the water quality model simulates the spatial and the temporal variation of the water quality, the nutrient species, and also dissolved oxygen. We have the phytoplankton dynamic considered in the water quality. We also have the sediment diagenesis. This is the hydrodynamic model. Hydrodynamic model was developed by USGS Woods Hole office. There are total 7 vertical layers. And for each layer, we have 160 times 800. So that's about 128,000 grade for each layer. And then we're using different source of data to set up the model, including the tidal forcing, and then the reading from the gauging stations, and also meteorological forces, and then the offshore forcing. So that's all the information we use to set up the hydrodynamic model. The hydrodynamic model simulates the temperature and the salinity. So this is on the left, that's the temperature. As you can see, it's about 4 degrees C higher than ocean in the shallow bay water. And this is before the shutdown of the power plant. That's the temperature simulate. That's before that power plant closure. On the right is the salinity distribution within the bay. So you can see that the lower salinity is in the northern Barnegat Bay area. That's to answer that question. This is the simulation to figure out what the residence time. What does that mean, the residence time? That means if a particle enter into the water body, how long it will take there to get out. So in average, it will be 13 days. But of course, it will vary by location. As you can see, the blue is the shorter residence time, and then the right will be a longer residence time. So we do have the largest residence time happen in the northern part of the bay, near Toms River, Kettle Creek. In the southern part of the bay, that is the Little Harbor Marsh Islands. So that's from this map, you see their residence time around like 30 days. The hydrodynamic model also simulates the water level. So when we have the simulation out, how did we know the model is doing a good job or not? That's we call calibration. So we compare the simulate result to the observed. So as you can see here from this plot, we have the data that's blue, and then the right, that's the simulate by the model. When we notice the observed data match the simulate well, that's the time we can see the model is well calibrated. Next, this is the water quality model. Water quality model was built using WASP model. It was developed by USGS West Trenton office. This one, we only have 3 vertical layers. And then for each layer, we have 609 grades. So it's much coarser compared to the hydrodynamic model. And we have a bunch of simulate parameters, including nitrogen species, phosphorus species, phytoplankton, silica, and BOD, and also chlorophyll A. To set up the model, we have to know what's the loading from various source. So that's the question. The major loading source from the monitoring subbasin, so where we use the collect data to collect the loading, to calculate the loading. And then we have the loading coming from the unmonitored subbasin. So that could be direct runoff or direct groundwater discharge or marsh estuary interaction. We also quantify the loading from atmosphere deposition. We also have the loading from the sediment, that is the benthic sediment flux. Of course, we have the loading from the ocean input from all 3 inlets. So we quantify all of them. This pie chart to give you idea was the distribution of the overall loading from various sources. 38% of the total nitrogen coming from the stream and the river, so this is the largest one. But the loading from the ocean inlet, that's also a big part. That is 29%. So that's the second largest one. For the water quality model, we did the same thing. We simulate the result compared to the observed. This is the total nitrogen concentration simulated for various stations, both surface and the bottom. So the predict one is the blue, and then the dot is the actual data we collected. So you can see that for some station, it matched very well, but for some station, there's some difference between the observed and then the simulated result. Another example is the water quality calibration is the chlorophyll A. Again, the simulate is the blue, and then the black dot is the observed. So that is calibration. But when can we say the model calibration is good enough? We have a model evaluation group formed in 2019. Their responsibility is to provide an independent, objective review to determine the adequacy of the calibration, the strengths and the weakness of the calibrated model, and then to see if the model can be used for the TMDL development or for the site-specific criteria development or for any other management decision-making. So we have 4 members. They are all experts in the hydrodynamic or water quality modeling for the estuary program. It took about 1 year for them to finish their review, and then each of them gave us their detailed comments. To summarize their comments, we received some good news or bad news. So the bad news is the model does not does not do a good job to catch the daily variability of the dissolved oxygen within the water body. And then the model cannot be used to address the turbidity. So remember those two assessment results, the DO and the turbidity. We are hoping to use the model to develop the TMDL for those. We cannot because the model does not do a good job for those two parameters. But they also gave a good news. They saying the model provide a reasonable representation of spatial and temporal distribution of salinity, nutrient, that's both total nitrogen and total phosphorus, and chlorophyll A. So when we see that comment, we are very happy. Why? Because even though we do not, right now, we don't have an existing total nitrogen criteria, but remember the research project. We have, under the Plan 9, Lanai just covered, we had 10 research projects. 3 of them, we call the bio-criteria project. So that's, highlight that's number 1, number 2, and the number 6 on this table. So that's bathymetry, benthic macroinvertebrate community evaluation, and then the diatom study, and then the phytoplankton. Those 3 biological indicator study, when we work on them, we were hoping to identify the level and the course of ecological impairment, and then to figure out if there are any correlation between the biological impairment with the water quality. So the water quality was focused on the nutrient, phosphorus or nitrogen. We did not get any promising result from the phytoplankton or diatom study, but we got very exciting result from the benthic macroinvertebrate study, which was done by Gary Tagon from Rutgers. So that project was done from 2012 to 2015, 4 years. And for each year, we collect the data from 100 locations within the bay. We collect the surface sediment sample, and then they analyze the species of the benthic macroinvertebrate. They group those species into 5 ecological group. So, and then one of the group we call the sensitive species group. For those species, that means they only survive with the normal water condition. So if there is a stress in the water condition, those species will not be happy. They will not be able to survive. We match the water quality data with the benthic macroinvertebrate station. So we group them. And so for the same station, we are able to do a stepwise linear regression on the water quality and then the abundance of the most sensitive species. That analysis gave us this correlation. This is a linear correlation. The x-axis is the average total nitrogen concentration in the water column. And then the y-axis is the proportion of the sensitive species. So after 4 years data, they developed this correlation and also they validate that correlation. As you can see, in order to have a good portion of sensitive species, we need to control the total nitrogen to be a certain level. Based on, we also look at other estuary program, and then we pick 450 microgram per liter, which is also 0.45 milligram per liter as the total nitrogen target, specifically for Barnegat Bay. If we can achieve that concentration, we hope that the sensitive species of benthic macroinvertebrate will be about 25%. So how does the concentration we observe from the bay compared to this 450 microgram per liter. This is the summary of the concentration we observed since 2014 to last year, 2022. BB04A, that's by the Toms River estuary. As you can see for that location, almost every single year, we have a concentration higher than that threshold. So on the map, that right line indicates that 450 microgram per liter. When we move to the central part of the bay, BB07A, the concentration much lower. We only have like a couple years with a spotty reading exceed that threshold. In the southern part of bay, BB09 or BB11, they gave us pretty much a similar information. So the concentration in general lower, but we do have some year with the concentration higher than that threshold. So that's the actual data tell us. Remember, the model also simulate what's going on within the bay, right? So this is the simulate concentration total nitrogen. As from the color, if you see any orange, the orange is 450 to 499 microgram per liter. And then you notice that northern part of bay, they have a total nitrogen concentration higher than 450. While in the southern part of bay, they're not in orange color, but they're in the right color. So that means they're in that edge to exceed that threshold. So if we want to achieve this specific target, 450 microgram per liter as the total nitrogen, we need to reduce the total nitrogen loading coming into the bay. How can we achieve that? We are going to reduce the loading from the source we can reduce. So we decide to require the reduction from both northern part of watershed and southern part of watershed. But we are not going to ask the same reduction from everywhere. We run different scenarios. So this table summarizes the result of the various simulation. The last one as a highlight there, that's 80% reduction from northern part of a watershed plus 20% reduction from southern part of a watershed. We will be able to achieve that 450 microgram per liter at every single assessment unit within the bay. So that's a total 9 assessment unit. So as the number indicate there, we will be able to achieve the concentration of total nitrogen less than 450 when we have that 80 and 20% reduction. So this will be the basis for us to develop the TMDL. That will be the guidance for us to work on to implement and then achieve the water quality target. This is the set specific target we developed for the Barnegat Bay. That's all I'm going to talk. Is there any additional question?
Here, I have a mic real quick. I'm coming to you. You go.
Thank you. Am I being heard?
Yeah.
I think the answer to my question was probably in your presentation, but I just didn't get it. You showed a pie chart, and it showed the percentages from various sectors of contributing nitrogen into Barnegat Bay. And it said that 29% is imported from the inlets. Is that 29% figure achieved by actual measurement? In other words, do we get it empirically, or is it built on a model?
When we set up the model, for the calibration, it was estimate using the actual data. So we did collect the sample from Barnegat Inlet, collect the sample from Little Egg Harbor Inlet. So those concentration was used to estimate the loading from the ocean.
And I think the answer to my question is there wasn't this kind of follow-up, but was there, and if there wasn't, why not, a follow-up by doing isotopic studies to find out where the nitrogen being imported by the inlets actually came from? Because it could be atmospheric deposition, or it could be from the sewage treatment plants coming back into the inlet, or it could be other sources. And I think that isotopic studies are how you get to the bottom of that. I know that the U.S. Geological Survey uses that method sometimes. Was that further study done or not? Because if it's from sewage treatment plants, then that could start us down the road of really getting some nitrogen out of Barnegat Bay.
Yeah, I think that's a good suggestion. I don't think we have those study done yet.
Yeah, I just want to build on Willie's question. Was that surprising that 29% was coming from the inlets?
You know, that's what the data tell us.
That's what, yeah, I know, but was anybody expecting that much of a loading from the inlets? Just curious. And the other question I have is, could you just explain the benthic nitrogen flux, the 14%, how that could explain what that loading is from? I'm assuming it's from sediment. But
Yes, that's from sediment. Yes, just like in this slide, with regarding the loading source, that's the 5 major ones. So this one is that's this one, the benthic sediment flux.
I guess I'd add a little wrinkle on that. You'd not only have to detect that stable isotope ratio, you'd have to pin it down to actual dischargers, which I think would present a more challenging question. Because of the stratification off the shore and some are a lot, New York Bight waters might upwell into the area, but the Ocean County dischargers are a pittance compared to the discharge by New Jersey and other states into the New York Bight. Oh, no, I'm not opposed to that. In fact, I think you and I have had this conversation a couple of times before. It's just, it becomes an interstate issue there. And it's just in terms of locally addressing that just becomes sort of a bigger picture question for the state and others. So I think it should be answered. It's just, it might be more of a challenge than any of us know.
Any other in-person questions?
Thank you. I'm just curious, like the higher nitrogen loading in the northern bay compared to the southern bay, is it more related to like higher residence time on the northern compared to southern, or is it more related to like the possible difference in terms of the input depending on the different region, like coming from the terrestrial, from the runoff or other things?
I think it's both. It's the loading from the tributary. And also we noticed that the Point Pleasant Canal coming in, that's also provide a higher concentration than the Barnegat Inlet and the Little Egg Harbor Inlet.
Good, thank you.
Is the report of the MEG publicly available?
You mean the benthic invertebrate
Well,
report?
MEG, remind me what MEG stands for.
Oh, sorry. No, we don't have that public available yet.
And will it become available publicly?
With the TMDL, yeah.
So it will be posted? And will all of the studies and all the documents, will everything that they used to come up with their comments also be publicly available and be posted?
Uh,
Well, I've been told that we have to talk into microphones because people who are listening remotely need to hear us.
When the department proposes the actual TMDL, all the supporting materials will be made publicly available, or access to them will be made publicly available.
Everything that the MEG took into account as it wrote its report?
Yes.
Thank
Yes.
you.
Okay, so we have a few questions online on the chat. I'll start with Christian Mancilla's question, which is submerged aquatic vegetation the end target of controlling turbidity?
I don't think it's only a turbidity issue.
Okay, so we have another question from George Murniak. What is sediment diagenesis in model?
Oh, that is that's the module of the model to simulate the benthic sediment flux.
Okay, thank you. And then Murray Rosenberg asked, were modeling scenarios for potential future impacts of climate change incorporated into the dynamic modeling?
I don't think so, but we could add that consideration that will impact the temperature.
Christian Mancilla asked, is the 0.45 milligrams per liter total nitrogen criteria not to exceed, or is there an exceedance frequency in the criteria?
Okay, yeah, I want to clarify this 450 microgram per liter is a seasonal average. So that is from July, I think it's on one of the slide. I include there, it's the concentration from July 1st to September 30. So that is the average period. So simply speaking, that is just the summer average. So if the concentration over that period of time exceed 450, that will be considered as a violation.
Thank you. Robert Nicholson asks, do loads from the Manasquan Inlet implicate a need to manage loads from the Manasquan watershed?
It's also a very good question. Yes. When we set up the future scenario for the reduction scenario, we assume the concentration from Point Pleasant Canal will be improved in the same situation as Barnegat Inlet and the Little Egg Harbor Inlet. Even though the observed concentration based on the actual data, the concentration at Point Pleasant Canal are definitely higher than Barnegat Inlet and Little Egg Harbor Inlet.
Thank you. And then another two from Christian. The first is, how did you account for the difference in hydrological years, meaning low flows, high flows, et cetera?
So flow, the model, the hydrodynamic model simulation period, that's the March through October of 2012. So when we look at the data, that year, it's kind of like a representative.
Thank you. And then, was there a significant reduction in sediment nutrient fluxes under the reduced load scenarios?
It's not a significant, but we were able to adjust the number based on some empirical model or empirical relationship.
Then from Charles Caruso, the 60-20 reduction for Tom's River appears to meet the 450 target. Is that reduction being considered for Tom's River rather than the overall bay target?
We don't have that kind of separation just for like a local assessment unit. So this 80-20 split, that's what we normally do, just, separate different regions.
Thank you. And the last question is from Paul Shore. How do historic loads from septics and SCPs discharged into back bays from 1970s get recognized in model, and how long will they take to be reduced?
That's depending on, the impact of those to the data we collect. If the impact of those still there, that should reflect in the concentration in the sample we collect that was considered when we set up the model.
Okay. And then, I'm sorry, one more from Paul Shore. What nitrogen targets for Delaware Bay or Chesapeake Bay? What are nitrogen targets for Delaware Bay or Chesapeake Bay?
I don't think there is a number for Delaware Bay. I don't think there is one yet.
Okay.
But Chesapeake Bay, it varies by region, so.
Okay, thank you. That was the last question from the chat.
Okay. Any other question? Okay, I think we're supposed to have a break.